It's kind of wild when you think about it. We have all this incredible technology, but some of our most advanced robots can be totally stopped by something as simple as a pile of rocks. So today, we're going to dig into how engineers are looking to nature to solve this exact problem, teaching these four-legged robots how to walk, run, and just navigate our world.
I mean, it's a strange thought, right? We've got rovers driving around on Mars, but back here on Earth, a robot on wheels can get completely stuck on terrain that you or I, or even a dog, could just walk over without a problem. It's this huge challenge in robotics, but the solution, well, it's surprisingly elegant.
And yeah, that brings us right to the heart of the whole thing. It's this classic engineering battle, wheels versus legs. Okay, so wheels are fantastic, don't get me wrong. On a smooth surface like a factory floor or a paved road, perfect. They're super efficient, they're simple, but the second you hit uneven ground or, any kind of obstacle, they just run into trouble. Legs, though, they're built for all that messy, complex stuff. They can step over things, they can adapt their footing on the fly, and they can maneuver in ways wheels just can't. And look, this isn't some small niche problem. There's a quote from Boston Dynamics, the pioneers in this field, that really puts it all into perspective. They said, wheeled vehicles can only access about half of the Earth's landmass. People and animals can travel almost anywhere. Just let that sink in for a second. Half the planet is basically off limits to our current wheeled robots. That's huge. So if animals have already cracked the code for getting around on all kinds of terrain, why would we try to reinvent the wheel or, in this case, the leg? It just makes sense, right? Engineers are looking to the ultimate expert, nature itself. And this is what we call the biomimicked solution. And boom, here it is. This right here is the student-built quadruped robot that's at the heart of our story today. By really studying the mechanics of how animals move, this engineering team created this really elegant, nature-inspired solution to that massive mobility problem we were just talking about. Now, this whole approach has a name. It's called biomimicry. And it's so important to get this. It's not just about making a robot look like a dog or a cat. Not at all. It's about digging in and understanding the deep engineering principles that nature has been perfecting for literally millions of years. It's kind of like how the design of a bird's wing inspired the airplane, right? In that same way, engineers are learning from the time-tested strategies of four-legged animals to build a way better robot. All right, so how do you actually build one of these things from the ground up? Let's take a look under the hood at its anatomy. So check this out. This gives us a really great look at the robot's skeleton. Over on the left, you see the whole thing, the fully assembled body, and then on the right, we're zooming in on just a single leg. And you'll notice the main parts are actually named after their biological counterparts, the femur and the tibia. I mean, that's biomimicry in action, right there, all the way down to the component level. Okay, so if the 3D printed parts are the skeleton, what about the muscles? Well, that's where these come in. The robot's movement is powered by 12 different servomotor actuators. You can think of them as these really sophisticated motors that sit right at the joints, and they're what give the robot its incredible range of motion. It's just like how our muscles contract and relax. So let's break down the weight of this thing. The 3D printed skeleton is actually the heaviest part, coming in at a kilogram. Then you've got the servo muscles adding another 720 grams. But get this, the brain, which is a super powerful little Raspberry Pi computer, is incredibly light, just 57 grams. Wow. All in, the whole robot weighs a pretty nimble 3 kilos, which is, about 6.6 pounds? Now, you don't just jump into building a machine this complex. It's not guesswork, it's a really methodical engineering journey. It all kicks off with a concept, a sketch. Then that sketch gets turned into a detailed digital model. And here's a really critical step. Virtual stress analysis. This is where engineers can find and fix any weak points in the design on the computer before they've even made a single physical part. Super smart. And only after all that do they move on to building and testing the real thing. Okay, so we've got the body, right? We've got the skeleton and the muscles, but how do you bring it to life? I mean, how does a collection of plastic and motors actually learn to walk? Well, that's where the digital brain comes in. Okay, so there's this term you've got to know, inverse kinematics. I know, it sounds super complex, but don't let the name scare you. Here's a simple version. Imagine the robot wants to place its foot on a very specific spot, let's say right on top of a rock. Inverse kinematics is basically the crazy complex math its brain does, like instantly, to figure out all the exact angles every single joint in its leg needs to move to get that foot right there. It's pretty amazing. So what does all that math actually get you? Well, it's pretty much the magic that turns this static object into a dynamic, moving machine. It's how the robot comes up with a stable walking pattern, what's called a gait. It's how it can adjust its footing on uneven ground or step clean over an obstacle. It's even how it can keep its balance if it stumbles or gets bumped. At the end of the day, the software is what gives all that hardware its almost animal-like grace and agility.
All right, so we've looked at the anatomy and we've looked at the brain. We have a pretty good idea of how this thing works. But the bigger question is, why? Why is a student project like this so incredibly important? To answer that, let's zoom out and look at the real-world impact.
Okay, get ready for this because this number might just be the most jaw-dropping part of the entire project. The total cost to build this pretty sophisticated prototype was just 35,000 Indian rupees. Now, for perspective, that is less than 500 US dollars. Seriously, let that sink in for a moment. And that incredibly low cost is a direct answer to the single biggest problem in legged robotics today. Just like the project report says, the current models out there are too expensive and not robust, not easily available. So by proving that you can build a really capable robot dog for under $500, this project just completely tears down the biggest barrier there is, accessibility.
You know, making these robots affordable, making them accessible, it unlocks a future that honestly we've mostly just seen in science fiction movies. Just imagine these things carefully navigating a collapsed building on a search and rescue mission. Or picture them precisely tending to crops out in a field. Or exploring deep mines and other hazardous places that are just too dangerous for people. I mean, from logistics and delivery to even healthcare, the potential is it's immense.
Now, we started this whole journey by looking to nature to solve a very human engineering problem. We took our inspiration from the animal kingdom to build a better machine. But as these machines start to become a real part of our world, it kind of leaves us with a fascinating final question. Nature inspired our technology, so what will that technology inspire in us?
Thanks so much for watching.